Now we are at the second part of the congestion and flow control in sensor networks. We have already, in the first part, we have already looked at the issues of congestion and flow control in sensor networks and what are the different solutions that are available, the list of all these different solutions, and we have already gone through the highlights of two very well known protocols for congestion control, the ESRT and the CODA protocol. Now we are going to look at few other protocols in and the highlights of them in the next few moments. So let us now start with the next protocol, which is the PSFQ protocol, the full form of which is pump slowly and fetch quickly. So this name, basically pump slowly, fetch quickly, says it all about what has to be done by PSFQ. So the motivation for the PSFQ is a few observations. The observations are like this, that the most sensor network applications, they do not require 100% reliability of packet delivery, and but for applications, example the retasking of sensors, they need reliable delivery. So in both of these cases, as you can see, that in the first case the data transmission takes place from the source nodes towards the sink node, and in the second case it is from the sink node towards the source node. So the goal of PSFQ is to provide lossless delivery, minimize control overhead, because the more number of control packets you send, the more control overhead. More control overhead means more energy consumption, and we have a highly energy constrained network. The sensor networks are highly energy constrained, and we want to minimize this kind of control overheads. The third goal is to provide delay guarantees for delivery to all the intended nodes. PSFQ's main principle of working is the slow and the fetch combination. Slow is the pumping, slow pumping, so slow data propagation in the network from the source node, and fetch is basically to offer enough time for hop by hop packet recovery. So if we first look at the scenario of packet transfer in a multi-hop scenario. So I have been talking about, I have been using the PDU term packet, but if we are talking about congestion and at the transport layer, we are talking about segments. So in this particular case, it is not packets, but segments if we are talking about transport layer. So so what I am doing is basically I am interchangeably using this name, packet or segment, etc., but basically they all mean the same thing, and so the concept does not change at all. So so if we are talking about a multi-hop packet forwarding scenario, we have something like this, as you can see in this figure. So we have 4 nodes, 1, 2, 3 and 4, and it is a multi-hop packet forwarding scenario from 1 towards 4. So let us say that this is the this is a scenario where there is no link loss, and how packet forwarding takes place. So this is how packet forwarding takes place. So first packet or segment 1 is sent to sink node 2, from 2 to 3, from 3 to 4 and so on. Then for 2 also the packet number 2, packet ID 2 also the similar kind of thing, for 3 again the similar kind of approach. So now let us say that we consider how it looks like when we have there is some packet loss. So in this particular example, we see that packet 1 is sent, 2 is then lost, and then when 3 is sent, 2 knows that after 1 it was expecting 2, this node 2 knows that after packet 1 it was expecting packet 2, and that has been lost, and it has received 3. Then it will do what? It will explicitly send a recovery message for 2, and this process will be followed in the next hop nodes as well. So everybody is going to send a explicit recovery message for 2 towards the source node through the intermediate nodes like this. and that basically leads to wastage of different resources. Too many recovery messages are being sent, so that is not very ideal. So the way it can be handled is that if 2 is lost, packet 2 is lost and 3 is received, so this 3 is going to be buffered, and then an explicit recovery message like before will be sent towards 1, and only after receiving 2, both the packets 2 that has been received successfully or correctly and the buffered one 3 will be sent towards the next hop neighbor. Okay. So this is how PSFQ basically recovers from errors. So it stores the packet 3 and then forwards both 2 and 3 on successful receipt of 2. Store and forward mechanism is followed for recovering from error in PSFQ. So there are 3 functions in PSFQ: pump, which talks about how the messages have to be pumped into the network and have to be relayed; error recovery, which is basically the fetch operation; and third is the reporting, which is basically about status reporting. So we have the PSFQ schedule, pump schedule. So we have a scenario like this. So 1 is received, then received by node 1, packet 1 is received by node 1, then it will send this packet 1 within a certain interval bounded by Tmin and Tmax. Okay. And the same thing is going to be repeated at node 2 as well. 1 is going to be forwarded, packet 1 is going to be forwarded by node 2 within a certain bound Tmin Tmax. So if the packet is not duplicated and packet receipts are in order and TTL is not 0, then cache and schedule for packet forwarding at time t, and that t is bounded by Tmin and Tmax. When loss is detected, then it is in the fetch mode. Okay. So this is how it looks like in this particular mode. So this node 2 explicitly fetches the packet on packet 2 on receipt of node 3 and non receipt of packet 3 and non receipt of packet 2. So then explicitly it will this will be fetched on receipt of the packet 2 at node 2. This will be sent forward within a certain time bound of Tmin Tmax. So losses like this are going to be aggregated through the fetch operation and sent. This is what PSFQ tries to do using their protocol. Now let us look at another suggestion by PSFQ, which is the proactive fetch. In this mechanism, as we can see that the last packet was not received, and then this node, it will wait for certain duration of time t proc, it will time out, and then it will send an explicit request, proactive fetch request for the last packet. Now we come to the last protocol that we are going to discuss in this course. So the last congestion control protocol, it is called the RCRT protocol. It is a rate controlled reliable transport protocol. This protocol, it reliably transports sensor data from many sources to one or more sinks without incurring congestion collapse at fair and efficient rate. So in this particular protocol, we are considering that not only one sink, you can even have multiple sinks as shown in the figure in front of you. So how does it work? This particular protocol, how does it work? So In this protocol, as we can see, there are few things that are controlled. First thing is that we have a source node, then we have a sink node. So, the source node basically reports the data towards the sink node at a particular rate, maybe r prime, and the sink also sends the requests in the other direction towards the source node in this manner. So, the sink node is particularly involved in these activities: congestion detection, rate adaptation and rate allocation, and also end-to-end loss recovery. The source node is also involved in the end-to-end loss recovery. So, unlike congestion detection, rate adaptation and rate allocation, which are basically controlled by the sink, the end-to-end loss detection, loss recovery is done by both the sink as well as the source node. So, each node in this particular protocol, it opens a connection to the sink first, like this manner. It opens a connection towards the sink. The sink tells each node the rate that has to be used. The sink will tell, this green colored arrow shows that the sink is informing about. So, first of all, what happens is the source node opening a connection to the sink. Sink will tell the source node that this is the rate that you are going to use for sending the data. Each source node sends the packets at that particular rate only. So, this is that rate, that r prime. So, that r prime rate was once again informed by the sink to the source node that you should send at this rate only. The sink detects the packet losses and initiates loss discovery. The sink monitors congestion and reassigns the sending rate to each node. The source node follows what the sink tells it to do. So, how the end-to-end loss recovery is done? So, this is done using couple of mechanisms. So, let us look at few of these features. The loss recovery mechanism is done with the help of two acknowledgements. One is the negative acknowledgement, and the other one is the cumulative acknowledgement. So, two acknowledgements, negative acknowledgements, the NAC and the CAC cumulative acknowledgement are taken care of. The help of these are taken care of in order to recover from loss. And the second is the end-to-end retransmission mechanism. In the end-to-end retransmission mechanism, we will see that end-to-end a packet is going to be retransmitted if there is some kind of loss that has been detected. So, there are a few other things also. There are two specific data structures that are used by this particular protocol. One is the out of order packet list, the second one is the missing list. So, these two are maintained, these two lists are maintained by this particular protocol. So, out of order packet list is about the packets, it is a list of packets which have been received out of order. So, this list is buffering those packets, and missing list is that it was expecting some packet and it got missed. So, the missing list has the list of all these missing packets. So, let us now look at how this particular protocol functions. So, what we have just witnessed is that a packet 1 was sent by the source node, it was sent by the source node and it was sent via the sink node to the application which is running on this particular network. Okay. So, the application is controlled through the sink node, right. So, as we can see that once it has been sent, it is also buffered at the source in the retransmit buffer. In the retransmit buffer, it has been buffered at the source node. This is done by this particular protocol, thinking that once it is sent, it does not know that the packet is going to be successfully delivered to the sink and the application or not. It might get dropped in between. So, it basically once it is sent, it will also keep a copy of it in the retransmit buffer. The sink node, what it will do is it will now it will now expect, once it has handled handled packet 1, it will now expect the second packet. So the second packet is sent, and let us say that it was dropped before it was received at the sink node. Source node had sent packet 2, but it got dropped in between and was not received by the sink node. Now mind you that the sink node is still expecting packet 2 to arrive. Now you see that what has happened in the retransmit buffer of the source node. In the retransmit buffer you have 1 and then 2. Now packet 3 comes, it has again been appended in the retransmit buffer. Now this packet 3, it was successfully delivered to the sink node, but the sink node basically does not accept it as such, and it does not send to the application layer. So what it does is, it will first send 2 to the missing list and then send 3 to the out of order packet list, because it was it did not accept 3 as such, because it was expecting packet 2 which did not arrive. So once 3 is sent and has been successfully received by the sink node, it is sent to the out of order packet list, and the missing list is populated with 2. Then from the sink towards the source, a cumulative acknowledgement for 1 is sent and a negative acknowledgement for 2 is sent. Then once that is done, you see, as the animation showed, that the source basically then sent packet 1, and then in both the missing list and the out of order packet list at the sink node, the packets 2 and 3, they were finally delivered from those lists to the application. And then this process continues, and what we have is a control mechanism by which successfully, error free, the packets can be delivered from the source node to the sink node and finally to the application which is running on top. So the congestion detection is done through an intuition that the network is not congested as long as end-to-end processes, end-to-end losses are repaired quickly enough. It uses, this particular protocol uses a time to recover loss as a congestion indicator. So so what it does is, it keeps track of a metric which is the exponential weighted moving average. So the exponent, so if we look at this particular formula, so so Li divided by Ri times Rtt, and an exponential weighted moving average of that is kept track of, where Li stands for the length of out of order packet plus the missing length, list length minus 1, and this product of Ri times Rtti denotes the expected number of packets in the particular time interval Rtt. So what we get is this expected weighted moving average, and this value gives the this parameter Ci. It is denoted, this moving average is denoted as Ci. So this particular protocol says that you maintain two thresholds, one is the L, the other one is the U. So two thresholds are maintained, L and U, lower and upper, and to denote how much is the congestion, Ci. So it is saying that the channel is underutilized if Ci is less than equal to, channel utilization is less than or equal to the lower threshold, and it is congested, the channel is congested if Ci is greater than or equal to the upper threshold. This protocol, it adopts the AIMT rate adaptation technique. AIMD stands for additive increase, multiplicative decrease. So, as we can see through these formulae, the rate is adaptively increased in this manner and it is decreased in this manner. So, if there is some kind of congestion etc., the rate is going to be multiplicatively decreased, and this is the multiplication factor MT. So, when are the rate adaptation decisions made? So, these are made only after when the previous decision has taken effect, and the next question is that how is this MT, this multiplicative factor, determined? This particular factor can be determined in this particular way. Let us see how. Let us say we have a source and we have a sink. The so when the channel is congested, the actual amount of traffic is going to be far greater than the source rate Ri that was deemed sustainable. So, let us say that the source sends at the particular rate Ri towards the sink, and the probability of the packet that is sent by the source to the sink being delivered at the sink, let it be Pi. So, the number of packets intuitively, number of packets over a time interval that are received at the sink is conceptually the product of Ri and Pi. These are the total number of packets that are received at the sink successfully. The ones that are lost are Ri times 1 minus Pi, and that is quite obvious because P is the probability of successful delivery of a packet. So, Ri times 1 minus Pi will be the number of packets that are lost. So, so what we do over here is calculate, we means this particular protocol, what it does is it calculates two things. One is the expected forward traffic, which is basically Ri over Pi, and the expected reverse traffic, which is Ri times 1 minus Pi over Pi. So, the sum of these, if we take, we get this particular term Ri prime t, which is equal to Ri by P plus Ri times 1 minus P by P. Okay. So, this one times RT. Okay. So, basically these two sums will lead to Ri over P plus Ri times 1 minus Pi divided by P will give 2 minus Pit by Pit times Ri. Okay. So, this particular entity 2 minus Pit by Pit is basically defined as 1 over Mt, and this is, you recall that this is the factor, the multiplicative factor that we attempted to calculate. So, this will give 1 over, this factor will give is the 1 over Mt. So, in other words, Mt will be equal to Pt over 2 minus Pt, and it has been analytically shown in the paper that if Mt is larger than 0.5, if Mt is larger than 0.5 for P greater than or equal to 0.67. So, this is something that has been established in the paper and we do not need to know how. So, a few concluding remarks. RCRT is a reliable transport protocol for wireless sensor networks. Centralized congestion control provides better perspective into the network, which enables better aggregate control of traffic and affords flexibility in rate allocation. And here are a few summarized points about transport. Because of the harsh conditions and severe constraints, it may be difficult to implement reliability in a hop by hop manner rather than end to end manner at either the MAC or the transport layer. For energy efficiency, it is best to avoid congestion entirely or have packet losses occur close to the source. Back pressure is a useful technique. When possible, scheduled solutions are preferable. So, here are the references once again. These references you had also seen when we saw the first part of at the end of the first part of congestion control in sensor networks. And as I said in the first part as well, here as well, some of these slides and particularly the simulation animations have been adopted from different sources. The sources are mentioned over here. Some of these PPTs are useful for this particular purpose, for getting access to these different resources, the slides that we have talked about. Some of the contents with minor modifications we have adopted from these particular references. Thank you.